Good morning, students. Let us start the class. I have shared the screen as well, and if at all you find any difficulty, later on anyhow I am going to post this recording into the YouTube channel and you can go through it. So in yesterday's class, I was discussing about this standard resistor values and I was telling about this E24 series. From 10 till 91, we have this number, which means 10 ohms is available, 1K is available, 100 ohms is available, 10K is available, 100K is available, like that it goes on. 1 mega ohms is available, 10 mega ohms is available, like that this goes on. After that we have 11, after that we have 12. So using these numbers, what they generally do is the manufacturers of the resistors, they manufacture these many standard 24 values. This is called 24 series. Similarly, we have E48 series also, where they manufacture 48 standard resistor values. As I told yesterday, as it is not possible to have all types of values, these are the values that are available in the market. So in your exams, if at all you get such exercises, when you work out a particular problem, whatever is the value you get, that itself you can write down there. In general, in our course, in our analog electronic circuits, there is no need of remembering these standard resistors and there is no usage also in our course. But in the next semester, you are going to study one course called linear integrated circuits, where even for the exam, standard resistor chart is going to be given to you. So you need not remember all these values, but you must be aware of these values. Let me proceed now. This is a small topic which is not there in the syllabus as such, but it is better that you understand what is meant by a data sheet. A manufacturer will give a data sheet and you must be knowing how to read the relevant data that is available in those data sheets. The transistors that can dissipate less than a watt, they are called as small signal transistors. Those which can dissipate more than a watt, they are called as power transistors. For example, in our regular amplifiers, pre-amplifier we have, middle stage amplifier we have, they are all going to handle power in milliwatts. So in such case, we can call those transistors as small signal transistors. But at the output stage, let us say we have a 8 ohm speaker or a 12 ohm speaker, and the speaker is going to draw a lot of current from the power supply. In such case, at the output stage, we need a power amplifier. Then such transistor is called as a power transistor because that particular transistor is going to dissipate more than 1 watt of power. Otherwise, in general, in electronics, we always use milliamperes and milliwatts and kilo ohms and microfarads in that way. So for a diode, you have a number called 1N4007. You would have used this particular type of diode in the physics lab as well in first year. So that 1N indicates a diode, 2N indicates transistor. And in the data sheet, there are some things called as VCEO, collector to emitter voltage with the base open. This is a breakdown voltage beyond which the device will fail. Similarly, there is one more voltage called EBEO, emitter base voltage with collector open. This is a reverse breakdown voltage as well. For an example, for 2N, 3N, 3904, VCEO is 40 volt, VCBO is 60 volt, VEBO is 6 volt, collector current is 200 milliampere maximum, power dissipation is 625 milliwatt maximum at 25 degrees centigrade. You should specifically note down that for a given temperature, there is that particular wattage. If the temperature increases, then the wattage needs to be reduced. Otherwise, the transistor's age will be reduced transistor will not sustain a longer life, because even materials are subjected to high power, and when they cannot withstand that high power, even the materials will break down. So beta is 100 at collector current at 10 milliampere, and VB is sat, base to emitter voltage in saturation is around 0.85 volts. Just recall whatever I told yesterday. Even though we say VBE is 0.7 for silicon in general, it need not be the same value for all the transistors, because transistor to transistor the characteristics differ. So you can see in this example, for this particular transistor 2N3904, VBE sat is 0.85 volt at collector current of 10 milliampere. VCE sat is 0.2 volt at IC equals 10 milliampere. Yesterday we solved some exercises and I told you ideally collector to emitter voltage is 0. Ideally when the transistor is completely switched on, between collector to emitter, ideally there should not be any resistance, and ideally there should not be a voltage drop across the transistor. That is what we expect. But practically the transistor is nothing but NPN, with P being very small, and we can visualize a single N region there. Whenever transistor is completely switched on, between collector to emitter, we can visualize a single N region, ignoring the base region, because base region is very small. That particular N region is nothing but a semiconductor, and that semiconductor will have its own finite resistance. Because of its own finite resistance, there can be a small voltage drop across the transistor also. So ideally it is not 0. So here the manufacturer says it is 0.2 volt at the collector current of 10 milliampere. All these are subjective values, means they are interdependent values. But for most of our calculation purpose, what we do is we take VBE as 0.7 only, and we take VCE sat as 0. Because this 0.2 volt, when we substitute in our formulae, it does not make much of a difference. Now there is something called power derating factor, which means if the temperature increases, then the power has to be reduced. Otherwise the transistor will not sustain a longer life. That is why for every 1 degree centigrade rise in temperature, 5 milliwatt power has to be reduced. This is what manufacturer says. Means, if let us say instead of 25 degree centigrade, if it is 26 degree centigrade, then this power of the transistor has to be reduced by 5 milliwatt. That means we should use it at 620 milliwatt only. That is the way how to design our circuitry. So, in general, a safety factor of 2 must be chosen. This means that if the PD max is 800 milliwatt, the BJD should not be utilized in more than 400 milliwatt. This is a thumb rule. The thumb rule says that any device is rated for maximum power, we should normally use it for only half of its power. We should not use it for its maximum power, because at that time also we are going to reduce its life. For example, let us say if I can handle 100 kg weight on my head, then I should not carry 100 kg weight every day. I can safely carry 50 kg weight every day. That means if my maximum capacity of lifting a load is 100 kg, I should not keep on lifting a load of 100 kg on daily basis. I can safely lift a load of 50 kg on a daily basis. That is how this is worked out. It is a thumb rule. Means any device, it has to be used for half of its maximum rating for a longer life. You can imagine your own cell phone or a laptop or a computer where there are integrated circuits and there are components. And even a mobile phone is going to draw 2 watts of power in general, 2 watts of RF power it is going to radiate. So it is powered by a battery, and battery is charged by a charger. Now the devices inside the cell phone should not be used at their maximum power. Reason is, when a cell phone is manufactured, the cell phone has to serve our purpose at least for next to 2 to 3 years or 4 to 5 years. Nowadays, anyhow, technology is changing rapidly. From 2G to 3G we came, from 3G to 4G we are moving. Technology is changing rapidly. But at least when we buy a product, we expect that at least let it serve us for 1 year, minimum 1 year. Later on, if we want to change, we can change. Otherwise, you can keep using the same product until the technology changes also. Even for the next 5 years also, you can keep using the same product there. Even the laptop or a mobile phone or whatever. So the thumb rule is what? The device which is utilized inside all these electronic systems should be utilized for only half of its maximum power. If it is dissipating heat on a daily basis every day, now the product will fail faster. In general, what happens is power dissipation, part of the power is dissipated at heat itself. More and more heat means it is less and less of life for the device. For this particular reason, we choose the device's power rating as half of the maximum power. Okay. Let me continue. In addition, if the case temperature exceeds 25 degrees centigrade, then either additional measures such as fan cooling or heat sink have to be utilized, or else the power has to be derated if temperature exceeds 25 degrees centigrade. Normally here what happens is all the devices are given their specific ratings at 25 degrees centigrade. That we generally take it as an ambient temperature, which is a average temperature throughout Earth. We sometimes call it as a normal temperature also. Now, if this temperature exceeds, what should we do? Either we should go for this power derating factor, but that is not enough. That is not enough. Only this power derating is not enough. Reason is the equipment is going to become hotter. When the equipment is going to become hotter, its ambient temperature itself is more, means it is going to affect all the devices which are within. So you can see that in every desktop computer system, inside that CPU unit, there is a fan working. As soon as you switch on, the fan will also switch on. Nowadays, even in some advanced laptops, there is a fan working inside. So this fan is going to cool the complete system. Otherwise, more and more of power which is dissipated by the system, it is going to reduce the age of the complete electronic system itself. You can see in the lab, in the regulated power supplies at the back side, you can see aluminum fins. All these aluminum fins are called as heat sinks. They are connected to that particular power transistor, which means when that power transistor is pumping or dissipating large amount of power, even its life is at risk. So the heat has to be dissipated to atmosphere. That is possible by means of connecting one more aluminum fin-like structure to the transistor, so that the aluminum structure will dissipate heat into the atmosphere. It is like if some person is having a fever, we can put one wet cloth on the head, so that head will not become much hotter because of the fever. Otherwise, the person may suffer some bigger problems such as fits or something like that. So, just like whenever the body temperature is more, we apply cool water on the face. Whenever during summer season, we apply fresh cool water on the face just to reduce the heat of our face. Same case is applicable to everything else on this earth, because even materials are subjected to heat. So if the heat increases, the material life also reduces. That is why we have to use heat sink. And or else the power has to be derated if the temperature exceeds 25 degree centigrade. If let us say fan cooling or heat sink is not at all possible inside, imagine that way. Now inside a mobile phone, fan cooling or heat sink is not possible, because a mobile phone is expected to be of lightweight. Mobile phone is expected to be portable. In such case, we cannot have a fan for a mobile phone. It is really funny. And we cannot have a heat sink for a mobile phone. If at all we connect a heat sink to the mobile phone, how do we handle it in our hand? Our hand will also burn. So it is actually not possible there. So the solution is what? Solution is use those devices with half power or sometimes even lesser. That is how circuits are designed. Let me proceed further. There is an example. I will not go through this example in detail because this is only for the sake of information. This actually is not there in syllabus. So the example, the BJT type number PZT3904 has a dissipation which is maximum 1000 milliwatt or 1 watt and the derating factor of 8 milliwatt per degree centigrade. Obtain the value of collector current which the device can safely withstand at 40 degree centigrade for VCE equals 10 volts. I have solved it already. Just look at this answer. Given PD max is 1 watt, nominal PD is 1 watt by 2 is 500 milliwatt. We have to use it as half of its power. As temperature is more than 25 degrees centigrade, the PD should be derated by 40 minus 25 into 8 milliwatt. This 40 minus 25, 25 is the ambient temperature. So this is the excess temperature. That is 120 milliwatt. So the PD at 40 degrees centigrade, power dissipation at 40 degrees centigrade is 500 minus 120 is 380 milliwatt. When VCE is 10 volts, IC is given by, you already know current is nothing but power divided by voltage. So 380 milliwatt divided by 10 is 38 milliamps. Just a minute, someone is waiting in the lobby, let me admit. Okay, let me proceed. That was about the data sheets. Now, there is something called variation in beta. This I had already told earlier. I am going to give a little more explanation here. The value of beta is specified in general, but in reality, it is not a constant. Its value varies in accordance with the construction of the transistor, the collector current, and the temperature. As I told you in one of the earlier classes that we do not have a human being who is quite identical to either me or you. We cannot find somebody identical to you or me on this whole earth because we are manufactured by nature in that way. Same way, when we manufacture transistors also, we don't have a control over the number of atoms which we are going to use as dopants. So it is not possible to manufacture two transistors having the same beta. There is going to be variation. And this beta is again dependent on the collector current and the temperature as well, because this temperature is the deciding factor for the movement of electrons. More the temperature, the electrons will have more energy to move. And that is when with the temperature, there can be variation in the characteristics of the transistor. So let us see, in practice, beta increases with increase in temperature. Further, no two BJTs will have the same beta under same condition due to the variations in the manufacturing process, which I have elaborated already. Hence, it is desirable to design the biasing circuits which are independent of beta. This is an important point. Yesterday, we worked out some exercises where beta is utilized for the calculations. But the calculations which we did in those exercises will change if at all we change a transistor. And as even the same type number transistor will not have the same beta. For example, let us say I use a transistor which is BC547. For that BC547, the manufacturer has given a range of beta. He will not give a single beta. He will give a range of beta, maybe 60 to 80 or maybe 120 to 140, sometimes 160 to 200. It's a range of values. Now you cannot really decide which value you have to use for your calculations. That is the reason it is always advisable that we have biasing circuitry which will not use beta. Now you may wonder today that how is it possible that without using beta, how can we calculate the collector current? It is possible because we engineers are going to design and develop such circuits only. As I told you other day, we have to keep on using the formula 4W1H rule. What, where, when, why, how. and we keep on getting questions, we keep on finding out solutions. Again, we will have some other problems. For those problems, we will keep on finding out solutions. That is how technology has evolved. If you visualize the technology which is prevalent in 2020, compare it with the technology in 2010, compare it with the technology in 2000 year itself, you will find a drastic change in every decade. Every 10 years, there has been a drastic improvement in technology. That is because of the work of the scientists as well as engineers. So later on in our syllabus, we are going to deal with the circuits which are going to have independence of beta. Means we will have a biasing circuit in which we are not going to use beta at all. Okay, that anyhow we are going to see later on. Let me proceed further. We will have some parameters in future. There is something called hybrid parameter. We are going to model the transistor by means of a hybrid parameter, which I am going to discuss later on. So in terms of hybrid parameters, beta is given the symbol HFE. H is for hybrid, F is for forward, and E is for emitter. So sometimes a manufacturer will not give the symbol beta directly. He will directly give the symbol HFE. HFE is a manufacturer's term, whereas beta is an engineer's term. You can take it that way. So with this introduction, let us understand one important concept called as load line. This you have to understand deeply now. This circuit we had seen yesterday. I will just annotate this particular circuit now. This particular circuit we had seen yesterday. This is called base bias or fixed bias. And we connect a capacitor here and we connect one more capacitor here. This capacitor we call it as CB, blocking capacitor. And here we connect one more capacitor, we call it as coupling capacitor. Otherwise, this RB and RC are utilized for biasing the transistor. What we want is, we want VC to be half of VCC, so that the transistor is exactly half on and half off. Then when we give a small signal here, transistor will gradually turn towards saturation or turns toward cutoff. That is when it is going to give a 180-degree phase shift, and we will have an amplified output voltage. This we had discussed in detail in the previous classes. Today let us see what is meant by a load line. Now this is the output characteristics which you are already familiar. We can have, in the x-axis we have VCE, that is the independent parameter, and in the y-axis we have IC, that is a dependent parameter, which means collector current is dependent on the collector to emitter voltage. Now this is the curve which is for each and every base current. If the IB1 is really very small, you can have a curve like this. Similarly, IB2, IB3, IB4 and IB5. IB5 is the maximum base current, for which you can have a curve like this. Now look at this particular curve. If the transistor is completely off, then the voltage at the collector is VCC. And if the transistor is completely on, then the voltage at the collector is ideally zero. Ideally zero. Even though I discussed that data sheet where it was mentioned as 0.2 volts, we can ignore it for all practical purposes. So we will say that VCE sat is 0. VCE sat is 0 means transistor is completely switched on. At that time, maximum collector current is flowing through the transistor. And let us say transistor is off. If the transistor is off, then VCE equals VCC, because all the voltage which is applied here is going to come through this resistor to this particular point at the collector. But it is not going to flow through the transistor because transistor is off. You imagine that way. Right now you just ignore the role of this RB because I am discussing the load line now. So if the transistor is off, current is 0, whereas voltage at the collector is maximum. You can see this point. current is 0, but voltage at the collector is maximum, that is VCC. Similarly, if the transistor is completely on, then the voltage across the transistor is 0 and the current is maximum. So, this IC max corresponds to saturation and this VCC corresponds to cutoff. In between, we have this active region. For a given IB1, you have this Q point here. You can see this Q point here. For IB2, Q point here. For IB3, Q point here. For IB4, Q point here. For IB5, Q point here. Q point is nothing but quiescent point, where the transistor is quiet and it is sensitive. So, if there is no RB at all, then the transistor is completely in the cutoff region. Let us say the transistor is given heavy current where RB is very less in value. RB is very less in value and IB is given sufficiently, so the transistor will completely switch on. If the transistor will completely switch on, then that is corresponding to the saturation region where collector current is maximum. But in analog electronic circuitry, we are going to use the transistor in the active region. When we are going to use the transistor in the active region, students have to join into the class earlier. When they keep on waiting in the lobby, it is already 9:35 now. So, from next class onwards, please join class on time. Okay, let me continue further. See, this IC max corresponds to saturation, this VCC corresponds to cutoff. Practically, where we have to use the transistor now? Somewhere here. Somewhere here. Let me try to annotate again. So, it is ideally, if the quiescent point is at the middle of the load line, then we can always say that the transistor is exactly in the middle of the active region, that is exactly half on, half off. So, now think about this. Now, if I am using the transistor exactly in the middle of the load line by choosing the value of RB and RC, in that case, I will have a line here and I will have a line horizontal here. Imagine from the Q point I draw a vertical line to x-axis and from the Q point I draw a horizontal line to y-axis. Then naturally this particular point at y-axis corresponds to IC max by 2 and this particular point at the x-axis corresponds to VCC by 2. So that VCC by 2 and IC max by 2 is the ideal coordinates for the quiescent point. Again, Rakesh is waiting in the lobby. From now on, I will tell the name of the student who is waiting in the lobby so that other students will know that who is the latecomer. Rakesh, from tomorrow onwards, join into class on time. Okay? Otherwise, you are going to lose a lot of information as far as the class is concerned. Let me continue now. When we set a Q point exactly here, this is now VCC by 2 and this is now IC max by 2. So, ideally, this is now VCC by 2. Let me write. This is now VCC by 2 and this is now IC max by 2. I am using the mouse itself for somehow doing annotation. Anyhow, it is only for temporary purpose, so it does not matter. So, this should be IC max by 2. So, if I write it this way, now the Q point should correspond to half of VCC, Q point should correspond to IC max by 2. Now, the point is, when we design the circuit, can we design that way? Yes, we can. IC max we can easily find out by VCC divided by RC itself is IC max. And VCC by 2 we already know. VCC we know, VCC by 2 we already know. So, choosing these two, we may have to choose this IC max on our own for a given design. Now, based on that, we can decide what must be the coordinates for a quiescent point. Based on that, we can choose the values of RB and RC. So that is why I told that this load line is a very important concept. I hope you understood. If at all you have any questions, you can put it in the chat box. Otherwise, I will continue. So what is load line? The load line is the graphical form of the operating points of the VJT. Understand this. Load line is the graphical form of the operating points. You can see this here. It is the graphical, okay. It is the graphical form for the operating points, which means the saturation point corresponds to IC max equals VCC by RC, and the cutoff point corresponds to IC equals 0 and VC equals VCC, which means transistor is off in this region where IC equals 0, and transistor is fully on where collector current is maximum. So based on this, the BJT operates in the active region in between. We can have different quiescent points for different values of IB. I have already told you. The slope of the load line is 1 over RC. By default, the slope of the load line is 1 over RC. Why? Because IC max is nothing but VCC by RC. When IC max is VCC by RC, naturally the slope of the load line is 1 over RC. So the manufacturer would have given this particular characteristic curve, and we will have to design this particular circuit using a transistor. So naturally we have to choose the values of RB and RC using these design criteria. There is a small exercise. Can you do it on your own? I will give you 2 minutes time. For the base bias circuit, the values of resistors are RB equals 470 kilo ohms, RC equals 2.2 kilo ohms. Plot the load line and identify the Q points for beta equals 50 and beta equals 80 given VCC equals 12 volts. Now beta equals 50 is given, RB, RC is given. Use all those knowledge which you gained yesterday and try to solve this problem within the next 2 or 3 minutes. I will be seeing the chat box for the correct answers. You don't have to do it for beta equals 80. Do it only for beta equals 50. I will show you the answers for beta equals 80. You can easily find out IB. IB is 12 minus 0.7 divided by 470 kilo ohms. VCC minus VBE divided by RB. Now when you find IB into beta is IC. You can find out that way. Okay, Sayan has given the answer. Quiescent point is, what is that? 6.2. Okay, 7 into 10 power 3. Okay, 6 volts and 2.7 milliampere. 6 volts and 2.7 milliampere. Let us see. Look at this now. 470K. So IC sat is how much? IC saturation you can find out directly 12 volts divided by 2.2K, because in saturation there will be no drop across the transistor. So IC sat is 5.45 milliampere. This we require for plotting the load line. And IB is 12 minus 0.7 divided by 470K, that is 24.04 microampere. So for beta equals 50, IC is 50 to 24.04 microampere is 1.2 milliampere. Let me see whether anybody has given the answer. Harshit Gowda has given the answer. Correct. It is 1.2 milliampere. Sayan, something went wrong with your calculations. Okay. So when beta is 50, IC is 50 into 24.04 microampere, 1.2 milliampere. So VCE is 12 minus ICRC. See, 12 volts minus ICRC is VCE. So 12 minus 1.2, 2.2 is 9.36 volts. When beta equals 80, IC is 80 into 24.04 microampere, and the current here is 1.92 milliampere. VCE is 12 minus same 1.1, 2.2. That milli and kilo I am not writing here because they are going to get cancelled out. So it is 7.78 volts. But Harshita has given the voltage as 9.34 for the earlier one. That is correct. For the second one, it is 1.92 milliampere and 7.78 volts. Now look at this and find out what went wrong. Thing went wrong in this design is beta can be different. When beta can be different, the Q point itself is different. The question is what? Why are we finding IB and then IC? Just to find out the difference which occurs because of beta. As I told you, it is not possible to have two transistors having the same beta. Manufacturer gives a range of, let us say, 40 to 80 as the beta. Now you can see, same type of transistor, same shop you buy, from the same shop, from the same packet, you take two transistors. They will have two different beta. Whenever the offline classes start, when you come to college, when you meet me, I will tell you, bring a multimeter. In the lab, I will give you two identical type number transistors. You check in the multimeter about the beta. Beta for those two transistors will be different. So why are we finding out this IC and VCE? To find out how much of variation happens in the Q point itself. You can see here, when beta is 50 with the same resistor values, when beta equals 50, VCE is 9.36 volt. When beta equals 80, VCE is 7.78 volts. That means there is a difference here. Even in current, 1.2 milliampere and 1.92 milliampere, there is a difference. In electronics, a minor difference also becomes major. In electronics, we cannot compromise on a smaller milliampere variation also, because why? A small milliampere variation is going to result in a much bigger variation of voltage as far as amplifiers are concerned. That is why this Q point is called as quiescent point, quietly sensitive point. Now ideally we should have a voltage here at 6 volts, and ideally we should have a current which is 5.4 milliampere by 2, right? Ideally the current during active region must be IC sat divided by 2. That is what the discussion of load line. IC sat divided by 2 is 5.45 milliampere divided by 2. It is around, let us say, 5.5 by 2. It is around 2.75 milliampere. But we are getting here 1.2 milliampere and 1.92 milliampere and ideally it was supposed to be 6 volts here, but we are getting here 9.36 volts and 7.78 volts for the given resistor values. So beta is going to give us lot of trouble now. We should have some circuitry which should not be dependent on beta. That way this base bias circuit we cannot use at all. This particular circuit which we have been discussing since yesterday, this circuit we cannot use at all in analog electronics. We can use this circuit in digital electronics as a NOT gate or as an inverter, but not as an amplifier. Okay. Now last 5 minutes is there. Let me show you this particular curve. This particular curve. Now using the same results, I have plotted this particular curve. Okay. What is that question? What is IC saturated? IC saturated means when the transistor is completely on, the current which is flowing through the transistor, that itself is called IC sat. What is 0.7? That means Nirmit was absent yesterday. 0.7 is the base to emitter voltage. Refer to the previous class videos. Between base to emitter there is a PN junction. So there is a 0.7 volt drop between base and emitter in the input side. That is why 0.7 is subtracted there. Those who are joining newly, you should refer to the previous class recordings. I will be again posting the class video, and I will be posting the YouTube channel's link in the Google class. You subscribe to that link, you will anyhow get the daily update. All of you can subscribe to that particular YouTube channel. Anyway, time is running out. I will have to finish faster now. Otherwise also I will revise this again in the next class. See, whatever exercise we did here, when the transistor is off, it is 12 volts. VCE equals VCC. When the transistor is completely on, it is IC sat, which is 5.45 milliampere. Now join those 2 points. This is the load line now. When you join those 2 points, now this is the load line. Now in this load line, we identified 2 Q points now. Based on beta equals 50 and beta equals 80, corresponding to these 2 values, we have this Q point. But ideally, we were supposed to have it here. Ideally, we were supposed to have it somewhere here. Around 2.75 milliampere should be the collector current in the active region, and 6 volts must be the voltage at the active region. But for the given RB and RC, and for the given value of beta, we have got these 2 Q points. So we engineers have a bigger responsibility to design accurate circuits so that they will work like faithful amplifiers. With this, I will conclude today's class. See you again in the next class. Until then, take care and bye-bye.